Okay, this is WebAssign 6C, number 21, and the problem read, 8,800 Newton shark is supported by a rope attached to a 3.2 meter rod that uh, that's, pivots at the base. Sorry. So I'll just draw a picture real quick. So the base pivots there. This is 20 degrees, 3.2 meters here, and shark is hanging here. If that's its weight force, 8,800 newtons, so it already gives us that. And we know that, so there's a cable here, so that means there's tension. And there is a force in the rod, this rod, so there's a force, like, I'll just call it like the F of R, or FR. Okay, and starting off, we know that it's in equilibrium, so that means that the net force is equal to 0, and that torque has to be equal to 0. So basically, like, ups have to equal to downs, left have to equal to rights, counterclockwise has to equal clockwise. So everything cancels out. So in part A, asks you to find the tension in the cable. So first, what I'd like to do is set up a torque equation. So we could do. So first we have to pick a pivot point. So we could use. I'll choose this point. So that cancels out the FR. And what I learned, like, while doing this problem is that wherever you pick your pivot point, like, all the forces acting, like, at that point, you can basically, like, forget about, because it kind of, like, takes away when you choose that pivot point. You're just focusing on the other forces. So since we want the tension force, we don't want to pick this point, because that means that force would, like, go out, and we won't be able to use that. So that's why we pick this one down here. So the tension force, or not tension force, sorry, the torque equation would look like, so we know that torque is equal to R times F times the sine of whatever angle. And also what I learned from this is that the angle you use in torque has to be the angle between whatever force you're using and then the R. It can't be like some random angle. It has to be the angle between R and the force. That's what I learned, and then that's where I kind of messed up when I was doing the problem, and probably a lot of people mess up is they don't know which angle to use. So this one will look like, so 3.2. This is the weight force of the shark, so times 8,800 newtons times the sine of 30. And we are using 30 because, oh sorry, I forgot to draw this in earlier. It gives us this angle 60, but since we want the angle between R, which would be this line, and the force here, we use this angle, because it's between R and our force. So that's why I use 30, and then minus, so those are all the downwards forces. And now for the upwards forces, we have the tension. So we're gonna subtract that one. So we do 3.2 for the R times tension, because we don't know that. We're gonna solve for tension, times sine of 80. This is all gonna equal 0 because one of the rules of equilibrium is that the net torque has to equal 0. So that means, like, so if we brought, like, this quantity to the other side, that way they would cancel out, because, like, they have to be equal to each other. So solve this for T. Oh yeah, so why I used 80 there was because this angle here, it gives you this 20, but it's kind of like a trap. Like, that's right, I used the wrong angle when I was doing this, and I didn't know what to do, so you want to use this big angle because it is the angle, you have to remember it is the angle between the force and R, the full angle, and this would be, since down here, so since this would be 30 here, this would have to be 60, and 60 plus 20 is 80, so it would be 80 degrees total. That's why I use 80 there. So, and then solving all of this out, we get that the tension force is equal to, and the problem says to round it to 3 sig figs, so, I'm sorry, 3 sig figs. So the tension force was equal to 4,470 newtons. And so, in part B and C both, so part B asks to find the horizontal force at the base of the rod, and the vertical, part C asks to find the vertical force. So, basically, I'll draw this over here. So this is F of R, this is the resultant force of the rod force, and it'd be, so, if you draw its components out, this is 60, so this would be F of R, cosine of 60 degrees, and this would be FR sine 60, opposite over hypotenuse. So, and now we can do our force equations. So, you could have done the force equations first, and then I think like did the torque equation, but I don't think it would have mattered. So x. So first we get to deal with them separately, the x and the y. So in the x direction, the left has to equal the right. So we have the left forces we have are the left force of the tension, which would be here, and then we have the right force of the F of R. So we can set those equal to each other. T cosine 20 would have to equal FR cosine 60. So, and we know our T, which we found up here in the first part, so we just plug that in and solve for FR, or it should be FRX, because FR in the X direction. So, solving this out, we get that FRX is equal to 4,198.4 newtons. And as for the direction, so that would be to the right. So that's why it's positive too, because we can call our direction up and to the right positive. So to the right. And now we do our y direction. So all the ups had equal the downs. So the up forces we have tension here. And then we have FRY over here, which we're solving for, and then we have the downward force of the shark, which is here. So, okay, so we have the force of the shark. I'll just call it like that. Is equal to the tension force, then y sine 20 plus FRY, the y component of the rod, sine 60. So, and we know T, and we know the shark's force, so we can just plug those in. Is equal to 4,470 sine 20 plus FRY sine 60. And solving all of this out for the y component of the rod, we get that it is equal to 7,271.9 newtons. And as for the direction, it'd be upwards. And that makes sense that it's upwards because it's positive. So those are your final answers there. So basically, something to watch out in this problem is that make sure that you're using the right angles, and so basically I learned like how to set up torque equations and how to use force and torque like together, kind of. I learned how to like pick a pivot point, and that the forces acting at that pivot point basically like go away, and it kind of helps you sometimes like to solve for other parts of the problem. So yeah,